When considering the place of origin of the universe prior to the Big Bang, and if there was no before, what was the cause of the Big Bang in the first place? Until a few centuries ago, the answer was easy. Some eternal deity set everything in motion. Even Isaac Newton believed that the universe was created by God some 6,000 years ago. Later, many scientists, including the young Albert Einstein, assumed the universe as a whole to be infinite and everlasting. Of course, stars could die, planets could collide, killing those who live there, and civilizations could arise and fall. But on large spatial scales and over long periods, it always looked roughly the same as it does now. In the 1930s, convincing evidence of the universe's expansion appeared. In the 1960s, evidence of its origin in the Big Bang was found. Such a radical revolution in the scientific worldview had not occurred since the recognition of the heliocentric system. But then two equally difficult questions arose. First, what actually was before the Big Bang? What was space like before it began to expand? And how long did it stay in this primordial state? Second, everything that has a beginning has an end. Therefore, at what point will our universe end? Brian Cox, an English physicist, set out to discover a solution to this question. In a world-shattering revelation, Professor Cox, a particle physicist, declared that he strongly suspects the universe existed before the Big Bang, putting the theory of our origins on its head. We used to think that the universe emerged in a state that was very hot and very dense at the beginning of time, what we called the Big Bang. However, we now have strong suspicions that the universe existed before that. In that sense, it's possible to speak of a time before the Big Bang. Come dig with us, deep into how Brian Cox just debunked the Big Bang. Professor Brian Cox has transformed his field of science in the 21st century into something accessible to everyone, consistently contributing to public debate and discussion. Never one to shy away from the big questions, the physicist previously took on the story of the Big Bang. The Big Bang concept first came about in the 1920s and 1930s, when astronomers observed something strange in distant galaxies. The farther away they were, the faster they appeared to be receding from us. According to predictions based on Einstein's relativity, a static universe would be gravitationally unstable. Everything had to move apart or collapse together. This apparent recession taught us that the universe was expanding. If things are getting farther apart as time goes on, it means they were closer together in the distant past. An expanding universe doesn't just mean that distances grow. It also means that the light within the universe stretches in wavelength as time passes. Since wavelength determines energy, this means the universe cools as it ages. As a result, things were hotter in the past. Extrapolate this back far enough, and you reach a time when everything was so hot that not even neutral atoms could form. If this picture were correct, there ought to be a lingering glow of radiation. Today, cooled to just a few degrees above absolute zero. This was discovered in 1964 by Arno Penzias and Bob Wilson, the cosmic microwave background, a breathtaking confirmation of the Big Bang. It's tempting, therefore, to keep extrapolating backwards to an even hotter, denser, more compact universe. If you keep going, you reach a point too hot for atomic nuclei to form, where radiation would blast apart any bound neutrons and protons. A time when matter-antimatter pairs could spontaneously form. A time when protons and neutrons broke down into a quark-gluon plasma. Rather than the emergence of time and space from a singular state, this sets up a different picture of the beginning of the Big Bang. Now, we can address the really big question: what does all of this mean for the true beginning of the universe, if it existed at all? The bottom line, the hot Big Bang definitely happened, but it doesn't extend all the way back to an arbitrarily hot, dense state. Instead, the universe's earliest days underwent a period of cosmic inflation, when space itself expanded at an extraordinary rate. Inflation ended and produced the fiery Big Bang, but did not create a singularity. What happened prior to inflation, or whether inflation was eternal to the past, is still unknown. But one certainty remains. The universe did not begin with the Big Bang. If there wasn't a Big Bang beginning, what was it? What happened? The short answer, we don't know. The long answer, it could have been many things, each mind-bending in its own way. One possibility is that before the Big Bang, the universe was an infinite stretch of ultra-hot dense material in a constant state until, for some reason, the Big Bang occurred. This pre-Big Bang universe may have been governed by quantum mechanics, the extremely small-scale physics. The Big Bang, then, would have marked the moment when classical physics took over as the dominant driver of the universe's evolution. For Stephen Hawking, prior to the Big Bang, events were immeasurable, and thus undefined. He called this the no-boundary proposal, in which time and space are finite but without boundaries, starting points or ending points, much like the Earth's surface is finite but has no edge, or there might have been something else before. The Big Bang worth pondering. Professor Brian Cox suggested there was a time before the Big Bang, a time in which the universe did not exist at all. He explored this in his documentary series Universe, stating that before the launch point of the Big Bang, there was no matter at all. All that existed was space-time and an ocean of energy, almost still, but gently rippling. This place, as he said, should be imagined as a near ocean of energy filling the void. It would have been devoid of structures, and the energy in the space would have caused it to violently stretch, something well known in the Bible as being flipped by inflation in space. Brian Cox turns the creation story on its head and continues to describe the scientific creation story. The crux of the story is an unprecedentedly violent expansion, that is, inflation. He said, "In the beginning, there was an ocean of energy that drove a phenomenon known as rapid space expansion. Inflation had an impact on the ocean. As inflation ended, the ocean of energy was converted into matter by the Big Bang, and the pattern of the ripples etched its mark on the universe as regions of slightly different density in the hydrogen and helium gas that formed shortly after the Big Bang. The denser regions of gas collapsed to form the first stars and the first galaxies. 9 billion years later, a new star formed in the Milky Way, the Sun. This star was joined by 8 planets, including Earth, and nearly 13.8 billion years after it, we emerged, blinking into the light at the beginning. Notably, Brian Cox is not the only one to make such an argument about the beginning of the universe. Remarkable theoretical physics research has revealed a possible window into the very early universe, showing that it may be just the latest iteration of a bang-bound cycle that has been going on for at least once and possibly forever. The study found that the physics we've learned about the early universe, a wonderfully complicated mishmash of general relativity and high-energy particle physics, can only go so far before we give up and attempt to push deeper into the first moments of our cosmos. The math gets harder and harder to solve until it simply fails. The main sign that we have terrain yet to be explored is the presence of a singularity, or a point of infinite density, at the beginning of the Big Bang. Taken at face value, this tells us that at one point the universe was squeezed into an infinitely small, inescapably dense point. This is absurd, and what it really tells us is that we need new physics to solve this problem. Our current toolkit just isn't good enough to save the day. We need something new, physics capable of handling gravity and the other forces merged. At extremely high energies, that is exactly what string theory claims to be. A model of physics capable of handling gravity and the other forces combined at ultra-high energies. This means that string theory claims it can explain the earliest moments of the universe. One of string theory's earliest notions is the ekpyrotic universe, a term originating from the Greek word for conflagration or fire. In this situation, what we call the Big Bang, was sparked by something else happening before it. The Big Bang was not a beginning, but one part of a larger process. Extending the ekpyrotic concept has led to a theory again motivated by cyclic cosmology, also known as string theory. Technically, the concept of a continually repeating universe is thousands of years old and predates modern physics. But string theory gave the idea firm mathematical grounding. The cyclic universe goes about exactly as you might imagine, continually, bouncing between big bangs and big crunches, potentially for eternity, both back in time and into the future. As cool as this sounds, the cyclic model in its earliest stages had difficulty matching observations, a significant issue when attempting to do science rather than just tell stories. The main obstacle was confirming our observations regarding the cosmic microwave background, the fossil light left over from when the universe dated back only 380,000 years. While we can't see directly past that wall of light, theoretically, tinkering with the infant cosmos's physics would affect that afterglow light pattern. This made it seem that a cyclic universe was a neat but incorrect idea. However, the ekpyrotic torch has been kept lit over the years. In recent times, many physicists have explored the wrinkles in the mathematics and uncovered some previously missed opportunities. These scientists study the theory of the Big Bounce, suggesting the universe is expanding and contracting, swinging back and forth in a massive big-picture timeline. Some bouncers think this happened just once, while others believe cyclical bouncing is what makes our universe. While the Big Bounce still requires large leaps that must be explained with generous scientific hand-waving, proponents claim that it is significantly less problematic than the Big Bang model, which they say is fatally flawed. The Big Bang, as told, relies on an idea called inflation. This field of cosmology, especially concerning the rapid expansion after the Big Bang, involves some grand and creative ideas. Critics of inflation theory argue that it's overly neat, possibly contrived. However, inflation suggests an infinite number of universes, with the one we can observe being just one isolated bubble among many. This challenges the idea of a singular beginning and prompts questions about what might lie beyond our own bubble. Alternatively, proponents of the Big Bounce theory suggest a cyclical universe, potentially offering a more comprehensive explanation without the need for a multiverse. This theory proposes that before the Big Bang, there was a separate universe, with entropy increasing towards the past, suggesting it's possible that time moves in the opposite direction from our own universe. This anti-universe idea might explain dark matter as a form of ghostly particle called a neutrino, unique to its own universe. Moreover, extending CPT's symmetry to the entire universe implies the existence of a mirror image cosmos, where every aspect of our universe changes parity and time is reversed. This twin universe, operating under the same fundamental symmetries, may be responsible for phenomena like dark matter and the expansion of the universe, without the need for periods of inflation. Ideas like these challenge traditional views of cosmology and suggest there is still much to explore and understand about the nature of our universe. The concept of a CPT mirror universe suggests it exists beyond our Big Bang, potentially before the beginning of our observable cosmos. Researchers propose several observable consequences. Neutrinos ought to have Majorana behavior, acting as their own antiparticles, and one neutrino species should be massless, a significant prediction that can be tested. If inflation never occurred, the universe would have naturally filled with particles, and the absence of primordial gravitational waves, if confirmed by experiments, could support this model. By comprehending the origin of the universe, we push the limits of our knowledge. We cannot know the initial state of the universe with certainty, which hinders our achievement of a complete scientific theory of everything. Progress has revealed a detailed cosmic history, but there are still gaps, like the nature of dark energy and dark matter. The initial cause remains a mystery. Humility in the face of the unknown is essential. Unlike supernatural explanations, scientific inquiry relies on evidence and data rather than faith.